Dream2Real allows robots to imagine a 3D goal state for manipulation using vision language models. To motivate this line of work in the long term, suppose you ask a future robot to tidy your kitchen. Before the robot grasps anything, it should probably figure out where should each object go, or what should the goal state be. Determining a good goal state requires following subtle semantic rules which are not explicitly in the user instruction. For example, cooking pans should be placed upside down in a dishwasher so that they wash properly. And we want the robot to generalize these semantic rules across many objects and scenes. This motivates the use of vision language models like Clip. By training on millions of captioned images from the internet, including images of tidy kitchens, Clip learns to predict how closely an image matches a text description. So the question we ask is, can we use these VLMs as a general visual prior to determine a goal state zero shot? In our prior work, DALI-Bot, we used a web-scale diffusion model to generate goal images zero shot. However, this approach was limited to 2D tabletop scenes. In Dream2Real, we addressed the difficult challenge of using 2D VLMs to determine goal states in 3D scenes. The key idea is this. First, the robot autonomously builds an editable object-level nerve of the scene. This allows it to render what the scene would look like if the objects were arranged differently. Next, it evaluates these sampled arrangements with a vision language model to see which goal pose best matches the user instruction. Finally, the robot uses this goal pose to execute the rearrangement in the real world. Let's go through how it works step by step. First, the robot autonomously scans the scene and breaks it down into objects using segmentation and object captioning. Once the user instruction is received, the robot knows which object it needs to move, so we can train an object-level nerve for that object. The nerve can train in just a few seconds and gives us photorealistic renders of the object in any given pose. Then, we sample many possible poses for the object and filter out poses which are in collision with the rest of the scene. Next, for each sampled object pose, we render the scene as if the object were in that pose. For each rendered image, we compute the clip similarity score between that image and the user's language instruction. This can be done efficiently in parallel for many sampled poses at once. We choose the highest scoring arrangement as the goal state. The final step is the robot execution. The object pose which led to the highest scoring render is the goal pose. The robot uses a pre-trained DexNet to grasp the object. Since the robot has built 3D models of the objects, we also use this for collision avoidance during motion planning, as the robot places the object into its goal pose.
Alright, so here is our experiment setup. We evaluate on 10 rearrangement tasks across 3 distinct real-world scenes, including shopping scene, food table scene, and shelf scene as shown in this figure. Here's our conclusions. Conclusion 1. Our system works in multitask scenes and is robust to distractors. It can also complete tasks zero shot. This is one task in the shopping scene and the user input is put the apple inside the blue and white ball. The left figure shows our heat map for final VLM scores. The lighter the color, the higher the score. The right dot means best score in this scene, which corresponds to the imagined goal state shown in the right figure. As you can see, the score is highest inside the ball, which means the VLM knows where to put the apple to best match the user requirement. The second user input is put the apple beside the blue and white ball. Since the user instruction is different, the heat map is different, and the VLM knows to put the apple beside the ball as expected. For this experiment using food table scene, we want to test whether Dream2Real can understand multi-object relations. The first task is to move the black ball to make a triangle. As you can see, our system places the black ball correctly. And here's a different requirement to make an X shape, which again works pretty well. You can see from the heat map that the VLM understands the multi-object relation and places the black ball neatly to complete the X shape. Here's our last conclusion, that Dream2Real does work with 6 dove poses. In this initial scene, the bottle is lying on the table, so besides the correct position, the VLM must figure out the best orientation using its visual prior. As shown in the first task where we want the robot to put the bottle to make the 3 bottles in a row, we can tell the imagined goal position is correct, and also it's upright, so the orientation is also correct. The second task is to put it in front of the book, and the last one is to put it up beside the plant. So, Dream2Real bridges the gap between 2D VLMs and 6-stop robotics manipulation. Let's look at some strengths and limitations of Dream2Real. First, the method uses VLM zero-shot, so it does not require any example arrangements or further training. Second, it works in 3D things and 6-stop poses. Third, it uses VLM to visually evaluate whether a rendered arrangement looks correct. It is not bottlenecked by having to convert the scene into a text or coordinate description. One limitation of Dream2Real is its running time, particularly for lower tolerance tasks where denser sampling of poses is required. In future work, this could be sped up by iteratively sampling and scoring. Dream2Real also inherits some limitations of current VLMs, for example back and forth behavior. However, this also means Dream2Real will improve as VLMs continue to improve. Feel free to check out our code and demo on our GitHub, which can be installed with just one command. For more videos, results, and details, please see our paper and website. Thank you.